So first of all, I start off with ADC. Now ADC is concrete analysis and design, or analysis design concrete, to be more exact. And the basic idea behind here is that you put in the geometry and the loads, ADC will give you the reinforcement. So nice and straightforward. Normal titles. So we do have so in ADC we have a number of design code options. You can see there quite a wide range, including quite a few Eurocodes with the national annexes, but also Indian, Hong Kong, British, Australian and American. These work for all the sections, where you've got the column design, beam design, rib slab and one-way solid slabs. Today I'm just going to look at the beam design, the column design. I'm going to skip over the slabs because the slabs, in the way the slabs work, is very similar to the beam design, so there's no point covering both of those. They're essentially the same, just subtle differences like slabs supported by walls rather than columns, but apart from that they're much the same. So let's have a look at beam design first in action. I'm going to type in some initial spans. Now the number of spans is one of the few things in the wizard that you can't change later. So if you need to add a span or take a span off, you basically need to rerun this, unfortunately. But the other aspects, such as span, individual span dimensions, we can change these individually in a minute. We just need to set them up to begin with. Again, section. We have a number of sections: rectangular, T, taper, general iron, taper T. We can set these individually per span, but at the moment we have a span, same section all the way along. And I'll take a taper T, just be more interesting than the usual rectangular section, and I'll give it a total, say 500 deep overall. A flange will count from the slab, a meter width, make the slab 250 thick, and the web tapering from 400 down to 300. We also need to set up some supports. So left hand support, I'll just make that free. The right hand support could be just pin support, or we could encaster. Let's fix it in. Along the spans as well, we can have simple supports, or we can have columns above and below. So let's pick some, let's say a rectangular column, and this column will apply stiffness to the multi-span beams and affect the bending moments therein, and we'll just make the upper and lower the same size. Other settings, self-weight. If you want the ADC beam design to take wind loads, you can tick this, so they provide lateral stability. You can choose to redistribute moments, and so on, and the various checks in there. And materials, you can set your concrete design codes and your reinforcement codes. Next stage, loadings. Apply some general loads onto these beams. Again, we can edit individual spans later on, or you could set the load on just one span as a first pass. Cover. Again, we can set the individual covers manually, or we can go to the cover code. This of course will vary depending on which design code you've got set, and we can take the relevant exposure class that then sets the covers accordingly. Sizes and limits. We have a default range of sizes, but we might say that we're not going to get 8mm bars from our suppliers, and so on. And then or we might say we've got some other bar size that our supplier might be able to include. So maybe you're working to a different manufacturer. Shall leave that out. Once you've got the range of bar sizes, you can then say what where you want different sizes used where. So top bars range between 16 and 40. The continuity maybe at 12. And then the bottom 16 to 40. Continuity again. Link sizes, bars in group and maximum layers. So for heavily reinforced sections, grouping the bars and so on. Spacing, in this case, access for the poker for compacting the concrete, and so on. And selection criteria, because this is a trapezoidal section, we've got the choice for trapezoidal or rectangular links, optional open and closed links, and so on. This, of course, will vary again depending on what type of section you have chosen. All context sensitive. So let's finish that, and we see there is our section, and we've got fixed support at this end, cantilever at this end, far too big a cantilever. So let's go and adjust this. So spans. First span, let's just drop that down to 2 meters, more sensible cantilever. And of course we can also adjust the sections as well. If I run the wizard, for example, I can click on the section and then go in and actually change the section for a particular span. Likewise, we can also go in and adjust the supports in the particular locations as well. We have the loads on there, and again, you can adjust just the loads on individual spans, add in wind loads, add in notional loads. Load factors already prescribed, but you can set your own load factors for the various patch loadings. Right, let us analyze this, and with the analysis we then get shear forces and bending moments. You notice from the envelope shape the patch loading has been in operation, and go for the design. Now we could have done the design, that would do the analysis at the same time anyway. So it's just designing those bars, choosing the right sections, no warnings, and let's have a look at the bars chosen, and let's look at the cross section as well. So zoom in a bit closer just by clicking on the span, and we see we've got in this cantilever a few bars top and bottom. There's the continuity, and so once we see we generally got 2 to 3 T16s throughout, which then take into account bending requirements and shear force requirements and so on. So here's the links as well, and we have the 3 spans, or 4 spans, sorry, with the reinforcement, which you can then print out. You can also get a textual output as well with the design for submitting to building control. So let's look at the beam design. Now the column design is slightly different in that for the column design, first of all, you've only got one single span, but also it does additional things such as when you apply an axial load, it will add on moments onto the column from the second order effects and the imperfection requirements, or the eccentricities, depending on which code, design code you're working to. Again, also additional checks for validation. Sometimes see if you've specified a column which is too short, columns have to be a minimum length, and so you might get an error there. Likewise, height to thickness ratio might make it too long. If you're confident, you can switch these checks off, but they are in your hands. Sections, different selection of sections for columns, rectangular or circular. Let's go for a circular section. Make it 450 diameter. And again, concrete grades, reinforcements. And now effective lengths. Now if I just set these effective lengths, but you can choose which how the effective length is calculated, or alternatively you can go in and set set it in a more detailed manner. Let's just take this option. Axial lows, let's 3000 on. I'm going to leave the moments off because then you'll see how ADC adds the additional moments in automatically. Size limits is the same as before, except slightly different dialog. Arrangements, now this is slightly different. With the set sections, it's asking you for the number of rings to choose from and the number of bars in a ring, and whether it's set to the cover or set to a diameter. If you're dealing with a square section, this dialog will be slightly different again, where it will give you a choice of potential bar arrangements. With the bar sizes and the number of arrangements here, AdSec ATC will look at each of the possible combinations of the bars and the arrangements, check them all for detailing requirements, compliance, and those that pass that will then give them on to the design check. Cover as before, but I'll just set it as default for the moment, and the checks, different set of checks this time for detailing and so on, min spacing, maximum spacing, etc. So here is one of our sections, and if I just go for the design at this point, we see out of the number of bars sections possible, 4 of them have failed. There's 4 failed, but we've actually got about a dozen options which actually pass the detailing rules, and you see there's at least 35 possible combinations. So in detail on these, so let's look at the results. And there's a design for each of the combinations, and down here we see for sections 1 and 2 and 11 and 21 have failed. They're showing up in red, and 31 is the section which passes with the minimum amount of reinforcements. All the ones in black also pass. So let's go back to here, and which one was it? 21. No, 31. Sorry. So this is our section which is the most efficient. And or we can choose a different section, but we can also then say look at how hard it's working. Let's look at the axial moment chart, and you see there's the axial moment chart curve. As long as we're within this boundary, we're okay, and it's automatically marked on that load combination onto the column to see where it falls. But you can see how much moment is also added on. So that's it. ADC is very popular, especially for ground beams and pile designs and column designs. Note that it's a simple approach, so you've got a restricted number of section choices. If you're always working within those, it's great and it's very useful. If you want to deviate away from the standards, it gets ADC is not the section design program for that. What you want then for the more unusual sections is AdSec. Now AdSec is a cross-section analysis tool, but it's designed to work for any cross-section, whether straight concrete, composites. You can do mega columns, concrete encased steel sections, and so on. But as an introduction, I'll just create a beam section. And the idea again with AdSec is that, well, ADC, you give the loads and the geometry, it will give you the reinforcement. With AdSec, you give it the geometry and the reinforcement, it will give you its load capacity. But also other information such as crack widths under given loads. So let's Euro section, and I'm going to take just a rectangular section, but you notice that the choice of sections is much larger with AdSec. And I'll just make it, say, 600 deep, 400 wide. Aggregate size to allow for bar spacings and so on, detailing. And whilst I can add in individual bars or lines of bars and so on, I'll just use the template and do a beam arrangement. Could do a column and a cover. Cover links. Now note that the links are there not to calculate shear reinforcement, because shear is a three-dimensional phenomenon, whereas this is purely a cross section. But they are there to position the main bars. I'll include some top bars. Let's say 3 T12s, and I'll take 4 bottom T25s. Can put these bars in pairs, can have additional rows, and so on. And I'll include a sidebar, which is T16, and it'll position these in the middle. Alternatively, if you have multiple bars, you can set the pitch, and so on. And there's our section, and here it is. So this is our beam section. Now we can use these NM axial moment charts to have a look at its capacity in this respect. So it's just calculating the NM chart, and we can see that ultimate state, it can take moments between about -170 and plus 450. No, sorry, 131 plus 430. If you're interested in it, you can export these chart points, but we're going to use the software to calculate these capacities in a little bit more detail. Likewise, if you say it's a column, have the moments in the two directions, biaxial moments, plus a range of axial loads. Let's say, what's its axial capacity? 4,000. So say 0 to 4,000 kilonewtons, step 1,000 kilonewtons. So I'll do 5 calculations, which will take a couple of moments. And so for the varying axial loads, as you can see, the different rings, these are the bending moments in the two directions that the section is capable of carrying. Well, so let's try that out. So let's reduce it down and add in some loads. Now I'm going to add in some dead and alive, or permanent and variable. So let's take lowercase 1 as 200 kilonewton meters and lowercase 2 as 100. It's a beam, so I'm not having any axial load. And then an ultimate limit state case, which is going to be 1.35 L1 plus 1.5 L2. And I could have pre-stressed some of the bars, but I'll leave that off. That's 1. So with this ULS analysis case set, I can then do a ULS load or ULS strength check. Now these are similar, except that ULS loads analyze the section for the given loads. Let's look at the results. And ULS strength calculates how strong the section is. So I'm not getting an error message. I'm not getting a message that says no solution found. So we know that the section is capable of carrying the applied moment. And see the applied moment, you see it's calculated there, and it's multiplied up, so we're carrying a moment of 420 kilonewton meters. And for that given load, there's the strain plane, and these are the stresses and strains in the concrete and the reinforcement at that applied moment. Now the other option is a ULS strength calculation, which calculates the capacity of the section. And we see here is the axial, here is the applied moment, and that is the moment capacity for that axial load. And so we see the section is running at about 90% utilization. Notice as well that the stresses and strains for the reinforcement and the concrete are not at the applied moment, but at the capacity moment. So at full capacity, these are the stresses and strains that we applied to that section. And we can also do serviceability limit state cases. For example, there's another chart which is the moment curvature and the moment secant. So moment curvature takes the range of moments, and as the moment increases, this is how the section curves. Or alternatively, change this to stiffness, and we can see this is the EI stiffness of the beam section. As the moment increases, we see the cracking occurs, reinforcement yielding, and so on, up until failure point at about 460. But of course, you can copy these points out, export the curve, and so on. If we look at do an SLS case, serviceability limit state case, I could just take L2, which is the live load, or I can take load case dead plus live, and take from there. So if we do these limit state cases, select all of those, look at the general results, and we can see for these two cases, stresses and strains in the concrete and reinforcement. But also, if we look down here, so the crack width calculations for just live load, which is 0.7 mil, but the dead and live load getting just shy of 0.3 millimeters. If we go back to the graphical view, we can see these are the bars which are at the highest strain with the highest cover. These are bars which are governing the worst case cracking, but we can see that we're still within 0.3 millimeters, so the cracking on those loads is okay. Now, as I mentioned, AdSec can do quite complicated sections. That's a simple one. If I just do another section in here, what I'll do this time is, rather than take one of these example sections, which might be an ellipse or a secant pile, let's take a perimeter section. Now, perimeter section, you actually define the corner coordinates of the section, and you can type them in. And define the section this way. We do have bridge beams which you can add in, but I happen to have drawn a core wall in AutoCAD first, or CAD, and so I'll just go and choose that core wall, and see it imports this DXF, which needs to be a closed polyline, and you can see there are the coordinates of the wall. And again, I could add in reinforcement directly, but there are a couple of options for doing this. Well, one is that if the bars have been drawn in AutoCAD as circles on a particular layer, you can import them into the section. Alternately, we have a tool to add perimeter bars, and what this will do is it takes the cover, takes links or laces depending on how you specify in this section, and we can then add in some bars. Now, it's a small section. I'm going to add in some big bars just so that you can see it in action easier. And we see that's out 50 more bars at 250 centers, offset all the way around from the surface of the concrete, and then we can analyze this and so on as before. Now GSA is our third program. This is a finite element analysis program, and I'll just take a flat slab that I've created previously, and then we can analyze this and design the slab reinforcement on here. Now in here I've got dead and live loads, permanent variable if you prefer, and I've also included some edge loads on here. Now edge loads are a bit tricky with 2D elements, but the trick here is that I have included some bar elements around the edge which tie in with the slab mesh, and because these are bars they have no bending strength, and there's quite a nominal cross section of about 1 millimeter squared, so they have virtually no axial strength either. So what they'll essentially do is they'll take this line load and apply it onto the slab without affecting the slab stiffness. And there are tools for that, for selecting nodes and then adding in a string of elements, or drawing one long element and use the split command to split it at the existing nodes on the mesh. I've also added in a link into these openings. So into the openings, if I just set my you can see where the column falls. I've put a link into that point, and so you don't get the very high peak moments over the column center line, because the columns in the analysis model are one-dimensional. They're like a pin, but in reality they do have sizes. Now let me just check that constraint. Okay, they're currently all. I'm just going to change those to pin all, so I don't get the moment transfer between the individual nodes themselves. Okay, so let's analyze this, and it's going to take a static linear analysis. It will do an analysis task for each of the two low cases, and which means we then get deflected diagrams, deflected shapes, and contours for the concrete. We also have maximum, minimum moments, and so on. But we're only interested in projected moments. Now, this is a projected moment for just the live load, but I want an ultimate limit state case. So, as it's linear analysis, I'm going to do a combination case of the dead and the live loads. And we just display that, and we see these are the moments that we're getting in the moments in the x direction, and the moments in the x direction are the moments which will be taken by the reinforcement in the x direction. This sometimes causes confusion. Likewise, in the y direction, we also got torsion moments on the slab. Oops, torsion moments. And then we have the wood alma, which is the projected moments plus the magnitude of the torsion, and you can see it increases things a little bit, and likewise we're going in the other direction. Now for the reinforcement design, that will take into account all these projected moments, the torsion moments, and any in-plane forces such as axial loads. So you can use this for core walls and so on. But first what we need to do is to specify the design code. And again, we have quite a range of design codes in there: American, Australian, British, European, Hong Kong, and Indian. Let me take the Eurocodes. United Kingdom. And I need to set the design properties, so it's slab design properties. And whilst I could set them up in the table, I will use the wizard because you can see everything at once. And I want to take code-based concrete, code-based bars, though you can set your own user-defined ones. Direction of the reinforcement, this is related to the element's x-axis. Defaults to parallel and perpendicular. Obviously you can set this to different angles to suit your particular structural requirements. Axis to surface, GSA is working out areas of bars rather than actual bars. So this is the distance from the centroid of the reinforcement to the surface of the concrete, which you'll need to calculate to take into account the cover and an estimate of what the bar size will be in the top and bottom directions, in the two directions. Minimum areas of reinforcement, you could set this to nothing. Like minimum steel is 390, not 309. Or alternatively, you could work out an area for a particular bar size, and then RC Slab will then just calculate patches where the bars exceed that amount. Once we have that set, let me put that up the top and this down the bottom. Oh no, this one, that's better. And let's look at the contour. Now the contours include the slab design, and when we activate this, it will go and do away with the design. But you notice also that it takes the automatic contours and it will specify some contours for you. Now these are based on typical bar sizes and spaces. You can change these as you wish. But let's apply that and see what it gives you. So it calculates the reinforcement for each of the elements, and it'll then give us the contours. There we go. And we can see generally the minimum steel, there are some patches in the A direction, which is parallel to X, where we get into compression steel on the bottom of the slab. Look in the other direction, again some compression steel around the columns, and some patches where we need additional reinforcement. Top bars, again, sort of hogging steel, and so on. Now let's take this diagram for example, and let's say that we're generally happy, but we want to try and avoid these patches of additional bars, reduce those areas down. And we've currently at the moment got a 300 thick slab. With the RC slab design, we can choose to override this slab thickness, but as part of the design, so it has no effect on the analysis, the bending moments and so on at this stage. But I'll just type in a 350 thick slab, so increase up to 50 mil, and let's see what difference it makes to the reinforcement. And you see it has reduced those areas of additional bars, but maybe not enough. Let's just try a 400. And we can see it's checking again. And we've just got one section of slightly lighter bars, but it's generally okay. So And if you're happy with this revise section, what we then need to do is to delete the results, go to our slab, to different properties, and change this to 400mm. Note the bending factor thickness. Take that override off, and then reanalyze. For the final checks, obviously this will affect the self-weight calculations. So let's just recalculate that. So it does the analysis, and you see it's doing the design. And okay, you see it's increased self-weight, so it hasn't increased the bars. So it's a little bit iterative, this. Now, when you've got the bar contours for the different load cases and so on that you're happy with, you can export these images as an image file. If you want to make sure it's set to a particular scale, let's say 1 to 200, then you can save the image at a particular scale. You can also either have full color contours, or if we change the contours to line contours, you can see then get the outline, which might be easier on the printout to scribble on. Alright, so that is a very quick introduction to our 3 concrete design programs.